All right, for all the possible bases of the exponential function, there is one that is the most convenient when we are going to be working with calculus. So let me show you kind of how we get to that natural number. So if you have heard of it before, the natural number e. So essentially how they got this number is by looking at the slope of the graph at different points. So sorry, with different bases. So we know that if y equals 2 to the x, we know our key point is 1, 0. Same with if the base is 3. What's our next key point? If x is 1, then 2 to the x is 2. If x is 1, then 3 to the x is 3. So 2 goes up like this and then decays on the left, and 3 goes up like this. So you can see that 3 is slightly sharper or steeper than 2. And what we can do is look at the slope of the point 0, 1. And the way that we do that, when we have a curve, we don't really have a straight line, we create a straight line that only touches the curve at the key point that we want. And that is what we call a tangent line. So I zoom in on my graph, and as best as I can, I'm going to create a green line that is a straight line, touches my graph at 0, 1, and I have to estimate what the slope of this graph is. Well, let's take a look. If this is 1 point, I can use this as the other. 1, 2, 3 is my run. 1, 2 is my rise. So my slope here is approximately not very convenient, but on my laptop with my hand, this is the best I can do, which is approximately 0.6666, or as our notebook suggests, it's approximately 0.7 when we have 2 as the base of our exponential function. I'm going to do the same thing with our exponential function at 3. We have a steeper graph here, so now I'm going to draw it kind of like that. I could probably even draw it steeper than that. I don't know. Let's try this way. Okay, so now let's compare 2 points on my pink line. Here's our key point. Here's a point that's close enough to see. Yeah, I don't think that's steep enough. Let's try again. We want it to be very close to the graph, but only touch the graph at 1 point. So let's see, 1, 2, 3, 1, 2, 3, 4. Okay, I did not draw a very good line, but that's all right. Rise over run is like this, and it ends up being slightly higher than what we got ahead. If I were doing this by hand, I would have a slightly better and more accurate slope. Most closely, the slope of the tangent at the point 0, 1 for the graph, 3 to the x, is approximately 1.1. So when 2 is the base, the slope is 0.7. When 3 is the base, the slope is 1.1. So E kind of came about when they discovered that if you put this as the base of the exponential function, then at our key point 0, 1, the slope is exactly equal to 1. So our exponential graph here has a key point 0, 1. The slope at that graph is exactly 1, so 1 up, 1 over. And it looks like a growth. So it's kind of halfway between 2 and 3 as the base. We call this, again, exponential growth. The domain of this graph is all reals. The range of this graph is that y is strictly greater than 0. And of course, we have the horizontal asymptote at y equals 0. This is a very key point. It becomes super important as we move forward through calculus. Also, when we do an inverse, so we're using the natural log rather than using the natural log and spelling it log with a base of e, we use ln for the natural log. We'll do a couple of examples here. So let's take a look at this transformation. I have 1/2 in front of the e to the x. I have a negative next to the x in the exponent, and I have a -1 on the outside. So lots of things going on here. This is telling me I have a vertical compression by 1/2. I have a reflection over the y-axis over here, and I'm moving down by 1. So if I look at my key coordinates, I have a negative x, y over 2 minus 1 is how I would draw this key point. Okay, base function e to the x is 0, 1, going up like this. If I reflect it over the y-axis, then I'm going to end up with a graph like this. If I compress it by 1, then I'm bringing this point down to the halfway mark. So rather than 0, 1, it is now 0, 1/2. And I'm bringing it down 1. So from positive half to negative half. So my intercept now is here. It's growing this way and this way. I have dropped my asymptote from 0 to -1. My intercept is at 0, -1/2. My horizontal asymptote is at y equals -1. My range is that y has to be greater than -1, and my domain maintains that x is still a real number. There we go. So we can still do transformations as we would with the regular functions. Now, could you find what is the x-intercept of this graph? If y is 0, 1 over 2 e to the negative x minus 1. What is x? Can we work backwards? The answer is yes, we can. We add 1 to both sides, so 1 equals 1 over 2 e to the negative x. We multiply both sides by 2, so we end up with 2 equals e to the negative x. We're going to take the log of both sides, but because here our base is e, we're going to take the ln of both sides, leaving us with negative x. So the x-intercept occurs at negative ln 2, and we can always throw this into our calculator. Negative ln is a number just underneath the log button. 2, enter. So we have an x-intercept at 0.69 negative. Can write it as a coordinate. There we go. Okay, so we can use logs and we can use exponentials to essentially solve equations backwards and forwards. Okay, last example. For what values of x will e to the x be greater than 1 million? Let's see if we can sort this out. E to the x must be greater than 1 million. Let's solve for x. Let us take the ln of both sides. If I say ln of this and ln of this, I end up with x on this side. And on the other side, ln of 1 million. 1, 2, 3, 1, 2, 3. So 6 zeros. Can stick that in our calculator. Ln of 1, 2, 3, 4, 5, 6. Enter. 13.8. So x has to be greater than 13.8. So in order to reach y equals 1 million, or I guess reach higher than y equals 1 million, we have to set x greater than 13.8. Or we can say e to the 14 will be greater than 1 million if we're looking for just 1 point. Something like that. Okay, so your homework for this section is as this is stated. You can omit number 2, 11, and 15 if you like. Some tips here for number 3 and 4. Use E. And the way to get E as your base, you're going to click on the second and then ln button. So on my calculator right here, second ln is how you get the E. Some calculators will also have it under the, or sorry, on top of the divide sign. So you could also, if I clear this, second divide sign will give you just the E. If you want E with a power on it, then you do second ln, and then it automatically has a spot for you to put the exponent. Either way works. All right, off you go. I'll see you Wednesday.